Gravity, gravitational pull, right? The further you get away, it's like an inverse square law. We talked a little bit about that. So vector fields in general look like this, possibly. They have the same. So I want you to realize what's going on here. There's a little difference between, huge difference actually, between scalar valued functions and vector valued functions. When I have a function like this from a while back, when I input some numbers, what kind of thing comes out? When I input numbers, if I tell you that's obviously the volume of something, right? It could represent volume. So if x is 2, y is 3, and z is 4, the answer is a number. It's a scalar. So that's when they say scalar valued functions. They mean the values that come out, the outputs will be scalars. So what kind of function is this? Yeah, for any inputs, the outputs are going to be vectors. So that's a vector value function. And what we're going to see in the next section, 14.2, is when you integrate one or the other one, how that works is going to be a little different than it should be. I mean, you're integrating two different kind of things. But they are alike enough to make it easy to remember how to do them. So a very simple example, and actually this comes back to the tornado idea, is if I have this guy. And to graph these things, there's a couple things you could do for yourself to make it easier to try to graph these things. One thing is really nice, I think you'll notice, in the homework, I think I gave maybe one or two of these problems that were in 3D, but most of these I'm going to do it are in 2D. 3D is hard enough, period, and then you want to try to draw little arrows pointing off in certain directions. In 3D, that's really hard to pull off, right? But in 2D, this is pretty simple. One way to do this is to kind of look for places where they're the same. What's really going on here, for example, just to give an example, is at the point 1, 1. At the point 1, 1, what's the value of f?
Negative 1, 1.
Yeah, the output, like we said earlier, is going to be a vector, right? So there's an input of a point. The output's going to be a vector, specifically negative y comma x, so negative 1, 1. And can somebody tell me what's the slope going to be there? Yeah, it's going to be y over x, which will be 1 over negative 1 is negative 1. So it's got like a negative 1 slope. And it's pointing in the negative 1, 1 direction. Starting at what point, of course?
1, 1.
1, 1. So here's how it all goes together. So you see the pictures in the book. You see the nifty little pictures, and you can kind of see there's one that looks like a tornado. There's one that looks like a river flowing, so forth. There's one that looks like air coming out, coming in front of a door. Ooh. How the hell do you put those together from scratch? Well, you make yourself a little more complicated table like this is one way to do it. And this is the way I would suggest to do it. Because we don't have a clue how the hell that looks when we just look at it. Because it's brand new to us. So let's just do like we did before. You don't know how something looks, throw some stuff in it. So at the point 1, 1, it's going to point in the negative 1, 1 direction. So it's going to point 1, this will be xy. So it's got a negative slope, and it's going to point negative 1, 1. So it's going to point like that. How's that doing? That's got a negative slope, right? Does that make sense so far? And actually, this tells you how to draw the thing. It's just that, remember the thing about vectors. Vectors have a standard notation, but in this one specifically must start at this point. So at the point 1, 1, the vector is pointing in that direction. And just to kind of double check yourself, you can calculate the slope, and that makes sense. It's got a negative 1 slope, right? How are we doing so far? Now we can do entire families of points. What about anything that's on the y-axis, for example? What kind of input would that be? Anything on the y-axis got to look like what? 0, comma y. Cool? And in that case, what's the f going to be? Negative y 0. I love it. And then what's the slope going to be? 0. Remember, slope is y over x. Cool. So that's 0. I love it. So then all along the y-axis, it's got to be pointing in the negative y direction, right? Negative y, well, not negative y direction. It's got to be pointing in the x direction at a magnitude of negative y. So for example, at this point here, it's going to have to be pointing this way, just to be more specific. So it's at the point 0, 1. It's going to be negative 1, 0. The slope is 0, but it's got to be pointing in the negative 1 back.
Can we divide by 0? That's gonna be
No, if I do on the x-axis, what's going to have to be true? They're going to have what kind of slope on the x-axis? Undefined slope on the x-axis, right?
you said y over x, right?
Yeah, y over x. X,
0.
y.
That's right.
Yeah, be careful. The insides of these can be whatever the hell they want to be, but it's always x, y. Right? The x piece can be dependent on y, the y piece can be dependent on x, but I don't care. There's still x comma y. Cool? So in this case, these definitely have 0 slopes. At 0, 2, the only difference is going to be it's going to be a little bit longer. It still has 0 slopes, but now it's just going to be a little bit longer. How are we doing so far? Brand new, I understand. Brand new stuff, right? It's kind of nifty to look at the pictures and you can see what the pictures mean, but how to put the picture together yourself is always a whole different story. So what about, like we just said, along the x-axis, it's going to be, in general, x, 0. So the output's going to be 0x. And the slope is going to be undefined or infinite. So for positive x's, I should have said this right here. Notice for positive y's, this thing is going to be pointing back. But for negative y's, it's going to be negative, negative. It's going to be pointing forward. And this is all going together with the idea that this is a rotation field. It has a definite spin to it, right? So for negative y inputs, it's going to be pointing in that direction. Same kind of idea here. For positive x inputs, it's going to be pointing in the positive y direction. For negative x inputs, it's going to be pointing in the negative x direction. So for this right here, it's going to be pointing straight up. And then it's going to get a little longer here, a little longer there. You guys see how this thing is now coming together? Right, this isn't the quickest thing in the world when you're brand new to it. But it's just like graphing x cubed for the first time. You don't have a freaking clue what the hell it looks like. So you got to make a table, and then now you know what the hell x cubed looks like. You don't have to graph it. You know it's going to look like that, something like that. Same idea here. So along the negative x's, so now if I put negative 1, 0 in there, for example, it'll be 0, negative 1. Still infinite slope. So at 1, negative 1, 0, it's going to be pointing down 1. This will be pointing down 2, down 3. Okay, cool. And then you get the picture that you get on the bottom of page 963. If you kind of put all that stuff together. Now, if you're looking at the bottom of page 963, can you tell me, do they have any that kind of match this? Do they have any that are actually sitting on the x-axis? The thing to be really careful about, the thing that I'm always worried about people not believing me, is, for example, there's one that's right here. 1, 2, 3, 4. That's like this. And they say, well, look, Jeff, that's not straight up and down. But it doesn't have to be. Where's it start? Here, right? So it's based on that point. When are they going to be straight up and down? When they're actually starting at a point that's on the x-axis. Cool? Okay, maybe. So now you can ask a silly question like, if I put a boat there, where's it going to go? If this is some kind of a motion of water, this is going to follow the, right? It's not going to go anywhere really. It's just going to stay on that circle. So a lot of times you see things called flow lines. Well, actually, I think I did a little bit of that last time. You just connect them. You don't draw the little arrows. You just connect them all, so it gives you a better visual of what's going on. So a whirlpool would actually look more like we'd expect it to, whereas this would just be concentric circles coming out. So if you start on a circle, you never get the hell off of it, right? Whereas this guy, you put him here, and he's going to maybe he'll spiral in or he'll spiral out. depending on which direction that's going? Okay, cool. And doesn't this have a definite direction? This has got an orientation. So when you start integrating stuff over vector fields, oh shit, what the hell does that mean? Then their orientation is going to totally change things. If this was spinning this way, my integral would probably be the negative of what it would have been otherwise. That kind of makes sense. Okay, maybe.
Is there like a positive, like counterclockwise positive, clockwise negative or something?
Yeah, things are normally based on, they start off in the book, the first few examples they do is based on counterclockwise, but they could have done it the other way. It really doesn't matter, to be honest. What matters is, if I'm coming into this and I'm about trying to go this way, then I can say, well, what contribution did this have to my motion? That's the kind of thing you can do, given a vector field. And I'm going against it. So the wind is pushing me. It's coming this way, and I'm going to walk this way. What's the wind going to do to me? It's going to work against me. So I'm going to probably have a negative integral over that. Whereas if I'm walking a little bit with it, it's helping me. I'm going to have a positive integral along that direction. So that's where we're headed. Okay. Let's see. So we're right now in 14.1. It's the real basics. You just have to go and graph a few of these. Work with a few given definitions of vector fields. There's the radial vector fields we talked about last time on page 964. And what do I mean when I say radial vector field? What kind of a vector field is it? What does it look like? Where is it pointing? Away from the center, right? I like it. Cool. Whereas circulation fields rotate around the center. They actually are at 90-degree angles to the radial field, isn't it? A radial field would be at 90-degree angle to the circulation field. Okay. How are we doing so far with all these? I'm trying to use the words over and over so they get less frequent. Let's see. I can't remember how far I made last time. I think we did a little example last time. I do want to get into an example from 3 dimensions. So if I were you, example 2 on page 964 is kind of flimsy. A real quick word about example 2. This is page 964. If C is a circle, what do you think is going to be true? What did I just say about the radial field? Let's define a radial field to be this. There's a radial field, right? In fact, what's interesting about that is, can anybody tell me something interesting about that radial field?
It's a unit vector that's orthogonal to that.
All right, too much there, but I like it. It's a unit vector, right, for one thing. They don't have to be, because remember, the little p could be up here, could be a cube before power, fifth power, whatever. This one happens to be a unit vector radial field. How is it going to relate to those circle images, the curves that I could draw? If it's a radial field, what does that mean? It looks like a starburst, right? So you can draw it, basically it looks like that. And they get bigger as you go away. Right, and it's going out this way too. Everything's rushing away from the center. So of course it's going to be how related to the circles I could draw. Yeah, orthogonal. It's going to have to be orthogonal. So if you look at example 2, they say, show that this is orthogonal. Well, of course it's going to be freaking orthogonal. That's silly. Right? But this, the radial field they give me, kind of give me, it's going to be this here, of course. And then I can look at what these guys look like, right, for circles. And if I do that, how do I find the line tangent to surface? Let's see. I think this is where I stopped last time. Oh. All right, cool. And here's a big thing. Here's something that's coming up. Is it a squared? It might be a squared. That would make more sense. Shit. Let me tell you this, something very practical, right? Because I know multivariable calculus is difficult because there's really big, heavy concepts but you always want to balance it out with some practicalities. One important skill you're going to want to develop, and you're going to need to develop, is how to write parametric equations for a given function. Right? So circles are really nice. Can somebody tell me how to write a parametric equation? We don't need a single anybody for a circle. What would that look like? What's a way to write a parametric equation? Maybe I'll stop you two.
Me?
No, sorry.
Oh.
Yeah, don't say anything. I mean, we know what's it best to write circles in? Which polar, right? So what would x be in this case? Be more specific than just the general definition of x. Yeah, so x would be a cosine theta. Y would be a sine theta. To capture the entire circle, I want theta to go from what to what?
Or 0 to 2 pi.
0 to 2 pi. Is that the only way to parametricize this? No. In fact, a really stupid way to do it would be a cosine theta squared and a sine theta squared. That would still work, but why would you do that to yourself? So there's actually an example coming up where they'll do that. It doesn't matter. As long as you pick something that actually picks up the entire picture and not more than the picture, right? You don't want to circle twice. You guys remember that? Depending on how you do your, if I said cosine 2 theta, theta would only have to go up to pi. If I go to 2 pi, then I'm going to draw that circle twice. And everything I'm going to do with it is going to be double what I want it to be. Does that make sense? So as long as your parametric equation captures the whole thing and only the whole thing, which almost sounds like the whole truth and nothing but the truth, then it's going to work, period. It's going to work with what we do. So it's kind of nice to know. There will be some that make it easier. There will be some that make it harder, as always, right? You want to pick the ones that make it easy, if you can. So this then looks like this. Right? That's r of theta in this case. So how do I find a tangent line? Thank God it's the same as always, really. Just slight differences for the multivariable piece. Take the derivative. So what's r prime going to be? Cool. Which, to come back for a second, to come back to x's and y's, what would that really look like then? And what's negative yx dotted with xy? Which would tell you that these circles are how related to these radial lines from the force, from the vector field. What's that? There you go. Cool. Not too bad. Right? So right now, though, I'm sure there's some of you guys that said, okay, the math looked pretty easy, but what the hell just happened? But we're going to do some more very specific problems, and we're going to focus on how to write the parametric version of the given function. Because if you can do that, then the intervals are actually pretty easy. It's just getting more used to remembering how this kind of going from here to there. Right? There's going to be a lot of lines that are normally pretty easy. Just got to remember how to write a line out in R of t notation. Right? Okay. So, and actually, come to think of it, I might have said something about this. In 3 dimensions, everything's basically the same. Basically, same idea. It's just that in 3 dimensions, it makes it easier to talk about something called a gradient field, right? And of course, how do you think I create a gradient field? Let me start us off here. Yeah, good. Given 5 scale value function. You can actually create a vector field. Remember, a vector field just says for any input, the output's going to be some kind of a vector dependent on those inputs. I mean, that's the idea, right? So it's actually a lot wider, it's more wide open than you think. So anything you can think of. So one way to create a vector field is just to take the gradient of some given function. Right? So assuming I'm in 3 dimensions, right? So that means phi is some kind of a function of x, y, and z. What would this be then? You don't have to be uber specific. Just what's it mean to take a gradient? Really is what I'm asking. What would this look like? Yeah. So this would be phi x, phi y, phi z. Coolness, right? Not too bad. And a little thing to get us ready for the future here. That means that this, some f, g, and h function. Right, there's nothing major there. I'm just saying f can be written as some function, which in this case is equal to phi x, phi y, phi z. Okay, the funky thing about this, and what's going to eventually become incredibly important. Think about this for a second. This means that this f was created by taking a what, basically? What does gradient really mean? It's kind of like the equivalent of just taking a basic derivative, right? But it's involving all these different directions I can go in. So won't integrals of functions that came from this be easier to do? Because integration is just doing the undoing possible differentiation, right? So if I have a function that I can show came from the differentiation of some other function, their integrals will be stupid easy, thank God. Because in general, these integrals are not all that easy, right? So a huge part of chapter 14 is, when can I prove that they're going to give me this, when can I prove that it came from some other function? And thank God it turns out that that's damn easy to show. So that's coming up, that's in our future. I just want to say that right now since we're introducing this. Let's see something interesting. Blah, 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 blah. Oh, so there's a good example on page 967. It's got this plate, and in the middle there's probably a heat source underneath it. So on page 967 there's a plate, and in the middle it's really red, and as you go out it goes down to blue. So the temperature's decreasing as you go out. So if the temperature is my vector field, then what is really going on, the temperature is like my scalar function. So if I define a vector field based on the gradient of my temperature, which direction will that gradient point? What type of vector field will I create? So let me take this out of here before I mess you guys up.
The one you did earlier with the circles and it going out?
Almost. Because what's the gradient have to do? What's the one thing we know about the gradient, the physical interpretation? It points in the direction of...
The function most rapidly increases.
Yeah, increases. So which way should these be pointing then?
Towards the heat.
Towards the heat, which is in the middle, right? So it's sort of like a reverse radial function, right? Everything's pointing towards the center then. So it's going to be like this. Everything's pointing towards the center. So that's a nifty application for this. Heat's then always going to flow in what direction? And I know some of you guys, if you hate physics, it's too bad, because a lot of this stuff is so much easier to understand when you have something physically happening. So what direction will heat flow? Will it flow in this direction? Yes, it flows off the cold. So heat's going to have to flow in this direction. Right? Because that'll be the direction of steepest descent of temperature. Right? So in this case, the heat's going to radiate out. So I think a little thing of sterno underneath some plate. You guys all know what sterno is? Right? You can make your own little fire. Okay, so there's a fire source sitting here. All the heat's going to radiate out. Once it hits that plate, it's going to start to radiate out along the plate. Okay. Maybe.
This is in 2 dimensions?
Yeah, I'm thinking 2-dimensional. Yeah. Of course, you got heat radiating up into the air, but for the moment, we're neglecting that. Yeah. Okay. So the homework in here, I mean, is really not going to be huge. I'm kind of talking a lot about stuff that's coming up in the section we're going to be talking about right now. So I don't want you to make it feel that there's a lot of stuff in this section. There really isn't. So this section, just looking at the homework, there's a few sketches of two-dimensional vector fields. Trust me, you're going to want to do that little enhanced table that I did earlier, that kind of thing, or you can develop your own method, but that's kind of the way I did it myself when I had to do these things. They're going to have some matching. They're going to give you a vector field and try to ask you to match it to the graph. They're going to give you something like page 969, number 18. That's a lot like the example we did earlier. So they give you, let's see one that's a little more interesting. Well, 18's fine. 18, they give you this here. And they give you this here. And they give you a little extra something. This is the normal to this curve. So this really, I mean, just to show you, the language gets in our way sometimes, but what's your gut reaction say about, is this tangential to this or is this orthogonal to this? And what do you do to really show that? Yeah, you dot f dot n, right? And if that comes out to be 0, then it's obviously orthogonal. How would you show that it's tangential? What's got to be true if two things are actually parallel then? One has to be a multiple of the other, right? So those are easy. You just got to kind of wade through the terminology. Those problems are easy. Most of the problems in this section should be relatively easy. It's old stuff just repackaged with new words. 21 through 24 are the three-dimensional vector fields, which I don't think I gave you too many, thank God, because those are not easy to draw. Blah, blah, blah. And then they ask you to calculate some gradient fields. You just got to take the gradient. Normally, most students love the gradient, which I totally understand. It's just derivatives. Okay, and that's really all there is. I didn't do too much else in there. So let's get into 14.2. There's no specific questions on anything. I don't know if you guys trust me. That 14.1 should actually be semi-easy, is what I'm hoping. Not the major in there yet. 14.2 is where we really just turn the corner, just to be completely honest. 14.2 is rather freaky, but it's, let me see if I can't make it a little bit easier to see what they're trying to do as we go into it. I really, when I have an interval to do like this, when I just want to find this area here, there are several reasons why that is easy, right? If they give me the function, here's f of x, and I want to find the area underneath there, what of course would we do? Take the interval from 0 to b f of x dx, right? And the reason it's so damn easy is because that is a well-defined direction, right? Change in x, and x is defined to be along that way. So what really sucks is when I have 3 dimensions and I don't have a straight line that I'm trying to integrate across. And why the hell would anybody want to do that? Because most things in the physical world don't travel in straight lines. So when I want to find out something about some particle going through a magnetic field or something, I'm going to have to integrate along this freaky ass little trajectory it takes, right? Too bad for me. So what happens here now is I end up with, I'm going to be brave, I end up with, well, let me see, where's my little sketch? Well, that's basically the same thing. Oh, there we go. Yeah, that looks great. All right, so you can see this in the book a little bit better, possibly. So here's a surface, right? Here's some kind of a z equal f of xy. Okay, that's cool. We're comfortable with that. right? You got a little roof sitting over our, and so here's the domain. If I drop this down, there's a domain down here that goes to it. What I'm really interested in then is, okay, let me see here. And then I'll get into all that. So here is roughly the domain that goes up to this. Okay, how you guys doing? Right? And the waviness is because the height changes as you go from point to point. And as we've seen stuff like that already. What gets interesting is, if I'm curious about finding the area between this line and its output there. So I really want to find that area there. So I like the way the book describes it as the area of that curtain, right? Because curtains can be all wibbly wobbly. So that's true about this. And you can see really, if I take this out and put it here, what I've really got is sort of like this axis that goes however it wants to. And then I got this thing, and I'm trying to figure out, okay, what's the area between that and that now? And why is it not easy? Because I don't have a dx. Every time I take a step, it's pointing in some other direction. Right? Sounds impossible, really. But what do we already have? Now this could be buried deep in our heads because we did talk about this back in chapter 11. What is it that points in the direction? So given some curve, here's some curve that I'm given. And here's some function, some piece of the function. So this is f evaluated along c. Are you guys cool with that? So that's all the heights for all the inputs that are on that curve. How are we doing so far? So we're all used to having a floor, which are all the inputs that go to my roof. Now I'm just saying there's a specific line on that floor, just those inputs, and how high they'll go, and then I want to find that area of that. Okay. And of course, right here, where normally somebody say, why the hell do you want to do that? You deal with it. So this is going to be, the thing that I really want to use is ds. And what was that s? What does that s really represent, thankfully, most of the time in mathematics? Who remembers? Here's a little formula, s equals r theta. Arc length. I like it. So this is the change in the arc length. So why does this work beautifully here? And this is actually, if you think about it, if it's a straight line, the arc length is just as easy to measure then, isn't it? I don't have to do anything weird. I don't have to bring in any Pythagorean theorem or whatever. It's a straight line. So a lot of what we're going to do today would reduce back to this if it was a straight line that I was looking at. But if it's a straight line I'm looking at, I don't have to do all this weirdness anyway. This is wibbly wobbly. So, how the hell are we going to do this? One thing I do want you to remember, this is actually from section 11.9. You see which, blah, blah, blah. I'm going to skip one. Yep. Let's see if you guys remember this. And actually, this is kind of cool. This is from 11.9. Now, who remembers the magnitude of r prime? What would that really represent if I'm talking about position? Like r is my position, it's tracking something. What would r prime, the magnitude of that, represent?
Speed.
Speed, right? Velocity if I wanted to give a direction, but speed because it's magnitude. I love it. And this is, of course, time. And what is speed times time? Distance. I love it. Shit, yeah. Right? So this is beautiful. This is perfect. We actually already did this back in 11.9, which is a funky little section that I really didn't want to cover too deep because we actually don't use the ideas in there too much. This is one we definitely do use. And I do think I did cover this a bit back in 11.9. So what I've really got then is this. To do this integral, and this is sort of like when we had integrals over a volume or over a region. So I have an integral over a curve. So I want this. If I'm not lucky enough to have the function defined in terms of the arc length. So for example, when we did the earlier problem with the circle, and we let x equal a cosine theta, y equal to a sine theta. Theta is a beautiful thing if I use it in radians, because that is exactly arc length. Remember that from a million years ago? That's what radians is. They actually measure the true arc length. But if I called it 2 theta, why did I do that to myself? Now I don't have arc length. I have twice what I really wanted, right? So I'm going to get through it twice as quickly. Do you guys follow me a little bit? Okay, a little tiny. So if I'm lucky enough that the arc length is what this guy uses, then I can just go ahead and do the integral, bam. Right? So if I'm going around a circle, if it's a circle I've got, and this curve could be anything. If it's a circle I've got, and it's defined intelligently, then I can just do the integral directly. 0 to 2 pi, throw the function in there, go to town. Right? That's easy. So let's do an example like that first. And then we'll look at what happens when it's not. Then we have to use this. So let's do one example like this. Example 1. And this is sort of like what I was talking about earlier, the temperature of the circular plate. So we have a circular plate. Is this. What was it now? There we go. Find the average temperature along the edge. Edge of the plate. Okay. What we're doing today, you can extend to finding something over the surface of something, which we're not going to have enough time to get into. But if we can do it around the edge of something, we can do it around the surface of something also. That's just one step up. Let's just stick with edges for right now. All right, so how do I intelligently parametricize this given edge? The edge would, of course, be just x squared plus y squared equals 1. So that would be, of course, using like we did earlier. Instead of a, though, I know it's 1, so I'm going to say x is cosine theta. In fact, let's say cosine t. And y is sine t. Now, just to double check, if I have arc length, and I do, of course, we know I've got arc length. That's what theta really is. I got t up there instead of theta, but still, that's what it really is. What would the length of this be? What would the speed be? So here's my x, y. What's the magnitude of the velocity if that's my r? What's r prime going to be? We did this one earlier. All right, like that. We did that one earlier. So what would the magnitude of that be?
1.
1. You get the beautiful, the most lovely trig identity ever. Sine squared plus cosine squared is 1. Right? So the magnitude of r prime is 1. Anytime that happens, you know you have arc length as a parameter. You know that's what you're working with. So now I can just do the integral directly. I'm going to go all the way around the edge. So on t, of course, we go from 0 to 2 pi. You put your function in, but what are you even going to do with it to really be able to use that? What did we just define based on our edge? We only want to use points from the edge. And how did we define our edge? We define it like this. So instead of 100 times x squared, what's x? Cosine. So it'll be 100 times cosine squared plus 2 sine squared det. Oh, why is it x? It should be t. And now you integrate that. And of course, who remembers how you integrate cosine squared and sine squared? You use that identity.
Minus double angle sine over 2.
Yeah. So cosine squared.
It's 1/2.
Oh, okay. So you guys, how do you remember it?
1/2 plus
1 plus
half
cosine.
Because it's the sine that's the minus. Cool. So sine squared would be 1/2 minus 1/2 cosine. Cool?
You substitute sine.
Yeah, now you put that in for sine, you put that in for cosine, you can integrate that.
Can we put down like the 2 sine squared into like sine squared plus sine squared?
Yes, cool. And then you can eliminate a cosine squared with a sine squared. So one thing you could do is cosine squared plus sine squared is 1, but you still have an extra sine squared. And then you really just have to use this guy. Love it. Cool. And that's going to happen when they use ellipses. It's basically it's not really an ellipse, but the function is actually looking sort of elliptical here in a way, because the coefficients aren't the same when the x squared and the y squared. So a lot of times you can break out however many is going to match up with this other guy, make 1 out of it, and then you see how much you have left. So you have less to kind of substitute for, thank God. Now I don't have to use both of these, I can use this one. Cool. And then the integral is not that evil to do. So we get to the answer, I think it's 300 pi. And now to get the average, they want the average temperature along the edge. What should I have to do? Well, the average temperature along the edge, well, how long is the edge? Which in this case is 2 pi, because it's a circle of radius 1, right? So if I divide that by 2 pi, I get 150. They didn't tell me what units, the dorks, but if it was Fahrenheit, 150 degrees Fahrenheit, Kelvin, that's a damn cold ass plate, but we'll leave that alone for the moment. Okay. But it's all about, notice how it's all about the line they give you, the curve, parametricize that, and then use what you just did in the function they want you to look at. That's the path. You take the curve they give you, you write it in terms of t or some s or whatever, some parameter, and then you use what you just created to plug into this. And then you throw your interval together and go to 10. Now here we were lucky, right? I said this first example was going to be nice because the parameter we used was the arc length. So what do you do when it's not the arc length? You skip that problem. No. You actually, the funny thing is, you just do a substitution. So instead of this, we do where this is ds, remember? And a to b is what t does. So this here would be a function of s. So if I'm lucky enough that the function I'm using, or I'm smart enough to put it together to be arc length, which isn't always easy or possible, then I don't have to do too much. I can just throw it in there and go to 10 like we just did. If I'm given something I don't want to mess with it much, or I can't parametricize it with the arc length, then I just have to throw things in terms of t, not s. You know, not arc length, but actually just this general parameter t, right? Over there, the t I was using happened to be arc length. Cool. I didn't have to do all this stuff. And in fact, I did do this stuff. Because what did we get for r prime over there? What did we get for r prime? 1. Right? So that's why that wouldn't affect anything then. That's why I don't have to take it into account if it is the arc length. This would just be 1 then. So this is my my factor that takes into account how quickly things are growing. It's my speed factor is what they call in the book. And really, this is kind of silly. If I have this, stay with me. What's the first thing you would do to do this interval? You do u sub. You substitute. So you say u is x squared. So du is 2x dx. So you see how this is, that is like this? That's how quickly a parabola is moving for each point, right? This is the slope of a parabola. So that's kind of like the speed of the parabola at a certain x value, right? So this idea that we're so familiar with and we should be kick-ass with, u sub, is actually the exact same idea we're using here. Just thankfully with this guy that we know from before. Okay, and it really is it's a lot like what we already do with U sub. It's basically the same exact idea. So let's do an example like that. An example where we have to be careful about R prime. Oh, let's see if I have one. Alright, that's kind of cheesy, but too bad. Let's try it out. So we're going to do that same exact problem that we just did, that I'm currently erasing. But instead of having an intelligent definition for my parametrization, however you say that now, we're instead going to have something stupid. We're going to have, so again, the region was this plate. It was a circle, radius 1. Temperature was this guy. But now we're going to use this to parametricize this. We're going to say it's going to be, oh, I forgot what it was already. Cosine t squared, sine t squared. Now, what does t have to be in order to go, in order for this to do what it's supposed to do? Right? To capture that whole circle, what does t have to be? T squared has to go from 0 to 2 pi. So, of course, t has to go from 0 to square root of 2 pi, right? The opposite. Because what do you put in here to get 2 pi? You put in there root 2 pi, don't you? Right? So depending on how you choose, or how it's given to you to use parameters, you have to figure out what are the limits on t to capture the whole picture. So in this case, t has got to go from 0 to root 2 pi. So here's a good illustration of two things. One, how to use this thing. And two, the fact that I don't care how you use your parameters. It shouldn't matter. As long as you actually capture the whole image, it shouldn't matter how you define your parameters. It shouldn't. So, here's my R. I have to calculate then, I have to change this to this. So I got to calculate R prime. So what's R prime going to be? Be careful about what's being squared here, right? It's not cosine squared, it's cosine t squared. So don't overdo this. What's the derivative of cosine? Negative sine, and then derivative of the inside? 2t. So you negative 2t sine t squared, and then you get 2t cosine t squared. So the trig is not being squared, it's the t that's being squared. Be careful. So what's the magnitude of this thing? And this is a good little review. To find the magnitude of anything written like a vector is easy.
It's going to be 2t.
You just square root the squares of the pieces, right? Pythagorean theorem. So square root of this thing squared. Screw each other. Let's see, 4t squared plus this thing squared. So you get square root of 4t squared sine t squared squared plus cosine t squared squared. And I chose to write it like that just because there's too many 2's in there. I don't want to write it by the side. But it's basically sine squared plus cosine squared is, of course, 1. Square root of 4t squared is 2t, because we know t is greater than 0. I don't have to worry about any absolute value crap. Okay. So what I really want you to get from what I'm doing right now is the process. How to attack a problem. They're going to give you a function, a temperature function, a density function, or whatever. They're going to ask you to do it along some curve. You take the curve, you write it in parameters, and you write it parametrically. Use what you just did. So how am I going to write this function now? Would be the next step. Right? I've defined what x and y are, now I have to rewrite this guy. And find what r prime is so you know what to put here at the end. So here we go. Integral from what to what? Square root of 2 pi. The function I'm integrating is 100 times x squared, which would be cosine t squared squared plus twice y squared. R prime is 2t dt. And you notice how it's, do you see how this kind of works together? This is one step away from what we just did here that I took away. That actually, I guess it was underneath this too. If I let u equal t squared, what's du? If u equals t squared, du is 2t dt. And then it's just the same integral we had before, right? You guys with me? And of course it's going to come out the same. So no matter how I do this, that is kind of going to come in and make it back to what it would have been if I would have been able to do it with arc length, which we can't always do. This is relatively easy. This is not that bad. Yet. Yeah.
This C, is that going to be given to you or do you have to figure out on your own?
The worst they would do is to tell you like the lines between this point and this point. Right, so let's do a problem like that. I'll show you. So either they're going to give it directly, like they did here, here. It's the edge of this, so they told me it was a circle. Or they're going to tell me along the curve y equal x squared or something, right?
Okay, wait. So for this one, around the edge of the circle, so you would have to come up with C yourself. You would have to go.
You'd be given C, but not parametrically. You'd have to come up with the parametric interpretation of it yourself. And that's always going to be true. Well,
and it's just around the
unless
circle,
they're really nice.
so that's why it's cosine t squared.
Yeah, and in this case, t squared was kind of a stupid choice.
Okay.
It's better to do cosine t sine t if you have a circle, right? Hell yeah, I'd do that if I had a circle. They didn't, but it just came out. It would come out to be the same integral as we had before. Once we do u sub, so it's going to be the same answer we had before, of course. Let's do one that's on a line between 2 points. Yeah, one here is not very interesting. Oh wait, here's something. Shoot. Later, yeah. Oh, here it is. Cool. Freaky. Let's just do this one. Example 3A. So they want me to integrate this on this line, on the line from where'd it go? 100 to 011. Okay. So how do you determine the? Basically, you just want to create the vector function for a line. You want to write it r of t equals something. Good. You subtract them to get what?
The direction.
The direction, the vector that's pointing from one to the other one, right? Because remember, a line is going to be a position vector, which is like the y-intercept in a way, plus a slope, which would be the direction vector, times t. Right? So it's a lot like mx plus b, if you remember that stuff. So a lot of stuff is coming backwards here now. So if I subtract them, and which way should I really subtract them? If I want to go from this to this, yeah, subtract this minus this, right? It's always the ending minus the initial. So then when I subtract these, this should really be vectors all. So yeah, I get negative 1, 1, 1. So that's my direction vector, which acts like a slope for me, right? That's what that really does. So then what's my line then? My C can then be written how? Where do I start?
1, 0, 0.
1, 0, 0. And I go
T.
that many steps, where each step is in that direction. Now the next part is, what does T have to be to capture the entire segment that I'm talking about? And this is pretty straightforward. I've defined it to start here and end here already. So, and just to double check, when T is 0, I have 1, 0, 0. When T is 1, I get 1 minus 1, 0, 1, 1, which is where I want to end up, right? So T, I want to go from 0 to 1. Okay, how are we doing so far? Sort of, can't tell. Alright, so T goes from, you guys have excellent poker faces and never play poker.
Wait, can you explain why it's just going from 0 to 1 again?
Anytime you have a line segment between 2 points, and you do it the way we just did it, we see how far apart those are. This really gives me the direction then. And I forced it to go from here to here by subtracting those two things. One of these, if I take one step, where this is my step, do you guys kind of see what I mean by that? A vector is like a step. It gives me a direction and a magnitude. So I can step this way, this big, you know. So by subtracting those two, that's exactly how far in the direction I need to go from here to here. So how many steps do I need? 1. So if I don't take any steps, where am I? At the beginning point. If I go up to 1 step away, I'm at the end point. Sweet. Right?
So if you double the values like negative 2, 2, 2.
You'd have to take half a step. I love it. So that would be how you can alter your parameter. And sometimes, that's a really kind of a bad example, but sometimes if you alter parameter a little bit, the interval is easier to do. So that'll come later. Yeah. Let's see. So now, what do I have to do next? Let's write this R of t a little bit better. How do you want to do it? 1 minus t, t, t. You guys see that? Just slamming those together. 1 minus t, t, and t. So that's how I can write my my given curve parametrically. What's the next step now?
Taking derivative.
Yeah, good. Take the derivative.
Negative 1, 1, 1.
Which is kind of silly, of course. You should know that's going to be the derivative because this is like my slope, right? This is just a line. Its derivative should be easy. And we already knew it. We knew that was the slope, right? So now I've got that guy. What else do I need? I know my limits. I know this guy. The last thing I need to do is to rewrite my given function using what I've defined here, right? So you always look at how you define this guy. This is what I'm calling x. This is what I'm calling y. This is what I'm calling z, right? And I really want you to think about this. I can only use inputs from where? Where are the only inputs I can use for this? What's the idea here? The only inputs I can use are on that line. So I'm going to go ahead and freaking plug the line in. Shit, right? Just be very direct about it. I can only use these points. All right, let me put them in there. You know, it kind of makes sense. So if I take my integral now and rewrite it, it's going to be from 0 to 1. X is 1 minus t. Y is t. Plus twice z is t. R prime is that guy. What's the magnitude? This is one thing I love. What's the magnitude of R prime? Root 3. I love it, right? Square root of 1 squared plus 1 squared plus 1 squared is root 3. dt. You guys see the process, which you have to go through to get there. And actually, I think the process is on that handout I gave. Yeah. Well, they took it down to 2 steps, which is neat, but it's basically all you have to do. Find a parametric